Hello, everyone, and we are going to start our second lecture. Today we are going to talk about Gaussian elimination. As you probably remember from the past lecture, we can convert a linear system of several equations into a matrix. If the system is homogeneous, usually it's a matrix of coefficients. If the system is not homogeneous, we are going to have augmented matrix of coefficients plus extra column of free parts. Let's imagine that we have just arbitrary system of three variables, three equations, okay? I'm going to label coefficients. So my variables are labeled as x, y, z. Because there are three of them, I'm not going to keep like x1, x2, x3. But generally speaking, if you have more than three, it's going to be more convenient. How do I label my coefficients? Coefficients are the numbers in front of my variables. Well, I keep the first index labeling the row. So row number 1, and it's going to be the first index 1, 1, 1 everywhere. And then number of the column is going to be second index. So the first column, third column, second column, third column. I'm going to keep this labeling for my all matrices. So if I kind of miss coefficients somewhere, you just know that I'm going to use a standard order of labeling coefficients, okay? So that's a system, right, which can be converted into augmented matrix. Which is going to look much, much smaller. So we have A11, A12, A13, A21, A22, A23, A31, A32, A33. And yeah, normally, guys, I know that in the book sometimes they're not going to put any separation between matrix of coefficient and the right side, but I'm going to do it just to keep it in mind that we are dealing with augmented matrix. So that's like a typical augmented matrix for 3 by 3 system, right? Now, we don't know the coefficients. Somebody is going to give them to us. We don't know C. Somebody is going to give them to us. But imagine that we somehow magically solve the system and somebody gives us the answer. And the answer looks like this. X equals 1, Y equals 2, and Z equals 3. Well, again, the coefficients can be set the way that we can get this. X equals 1, 2, 3. Not important. If I convert them, these three solutions, that's actually a solution, right? But on the other hand, it's just like three equations, right? Equation number 1, equation number 2, equation number 3. If I convert it into augmented matrix, how it's going to look? Well, because the coefficient of x equals 1, and the coefficient of x is like a11, right? In the first equation, I'm going to put 1. There is no y and z in the first equation, so I'm going to put 0, 0. And my right side over here is equal to 1. I'm going to copy y here, right? So there is no x, 0 in front of x, 1 in front of y, 0 in front of z, and 2 at the right side. And the last one, 0 for x, 0 for y, 1 for z, and 3 for right side. You see that solution can be considered as three equations, and these three equations can be converted into augmented matrix. What is the difference between augmented matrix we have as a solution and as like a system, original system? Well, if you compare them, first, we do have certain values for C's, right? C1, C2, C3 are given, right? But normally they will be given if you start solving system of equations. The biggest difference is that coefficients A can be like basically anything here. But in our solution, coefficients are ones on main diagonal. I'm going to kind of maybe label them, call them main diagonal. And what we have above main diagonal and below main diagonal are just zeros, right? Do you see? So what does it mean? Well, it means that if you can't convert somehow your original matrix, which corresponds to your original system, using row operations, I'm going to talk about them again one more time, to this matrix, there is a way to convert it. That's going to give us a solution. Now, let's refresh what are row operations. Normally, guys, how do we solve system of equations? Well, we can use substitution, elimination methods, right? We can add two equations to eliminate a variable, and then we can do substitution. Those methods can be converted into row operations. You probably remember last class we considered three basic row operations. I'm going to review them one more time. And they correspond actually to the actions or math manipulations we can do with the original system. So number one, what we can do? We can multiply a row. And for those who forgot what is a row, oh, sorry, this is too wide, way too wide. Let me get that narrower. Oh, that's strange that I have it like on 6. So this is again row, and this is called column. First row operation, we can multiply the whole row by non-zero constant. So multiply row by a non-zero constant. Second operation, what we can do? Interchange two equations or interchange two rows. For example, we can interchange row number 1 and row number 3. Put row number 3 on top, row number 1 on the bottom. For system of equations, it's going to be just like you put first equation as the last one and last as the first one, which is not going to change our solution, right? And the last one, we can add or subtract equations. I'm going to just put add rows. Well, before you add rows, you can multiply them by any non-zero constant. So it's kind of combination, addition plus like multiplication. That's what we can do. So operations which we can normally do with system of equations for matrices are called row operations, right? The form we have where we have only ones on main diagonals and zeros everywhere else is called reduced row echelon form. Maybe I should label it over here, but like I'm going to force first row. So the form where we have ones on main diagonal and all zeros below and above main diagonal is called a reduced row echelon form. Sometimes you are going to see in the book as REF, reduced row echelon form. It's just like shorter way to say this, right? Do we have non-reduced row echelon form? Yes, guys. If you have ones on main diagonal, but not all elements above main diagonal are zeros, we are going to just call it a row echelon form. So reduced is talking about the zeros above main diagonal. If there are no zeros, they are just going to be row echelon form. Below main diagonals necessary for any like row echelon form. Okay. So basically our task is to take a matrix of the system, do these row operations, and bring it to reduced row echelon form. That's basically going to be converted right away into solution, right? Before we start working with real matrices, let's consider one more time possibilities for the final answer. Like how unique solution is going to look, how no solutions is going to look, or how infinitely many solutions is going to look, just before we start actually working on real matrices. Because it's important to understand, like, when you bring your matrix to reduced row echelon form, like how many solutions you have, or do you have any solutions. So number of solutions. And that's kind of important question in algebra. So number one, unique solution. How it's going to look, how reduced row echelon form is going to look when you have unique solution. 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 2, 3. So this is exactly how unique solution is going to look, and you are going to have x equals 1, y equals 2, and z equals 3. So if you end up with all ones on main diagonals, zeros below, zeros above, and some numbers on your right side, that's going to produce exactly one solution. Now we know that there are cases of no solutions. No solution. How no solution matrix is going to look. Typical example of no solution matrix is going to look like this. Of course, if you have more variables or more equations, it's going to look slightly different, but you do your reduction using row operations, and eventually you end up with a matrix which has a row of zeros, you see over here. But right side over here is not equal to 0. Why? The system is going to have no solution. Well, imagine that we write down the last row as equation. We're going to have 0 multiplied by x, 0 multiplied by y, plus 0 multiplied by z equals 3. Can we find out x, y, and z to multiply them by zeros and get 3? Of course not, because anything multiplied by 0 is going to produce 0, so it's never true. Never true for no x, y, z. No x, y, z. So that's how no solution matrix is going to look. Last case, infinitely many solutions, and how it's going to look. Infinitely many solutions. Well, it can look like this. So imagine that you get this row of zeros at the very bottom, but right side is equal to 0. What does it mean? How it's going to end up with infinitely many solutions? Well, let's look at the first equation. First equation is going to produce x equals 1, right? Second equation is going to produce y equals 2. What third equation is going to produce? Third equation is going to produce 0 multiplied by x plus 0 multiplied by y plus 0 multiplied by z equals 0. We already know that x equals 1 and y equals 2. So this element is 0, this element is 0. And we do know that this element, no matter what is z, is going to be 0 too. So the sum of these three zeros, of course, is always equal to 0. So this equation is always true for any x. Or for any z, sorry. So we can use z as a parameter. We can say that z equals t, where t belongs to real numbers. And that's going to produce parametric solutions for us. And final solution in this case is going to look like 1, 2, t. And actually, we can have something more complicated if you kind of have more equations, more variables, or more zero rows. Okay, but that's a typical case of infinitely many solutions. Okay, is 0, 0, 0 a solution? Well, if we deal with homogeneous system which has zeros over here, let me consider that's going to be case number 4. If you deal with homogeneous system and you end up with the next matrix. So this is homogeneous system. Remember that homogeneous system has all zeros on the right side. Non-homogeneous can have numbers. So how this one is going to look? This homogeneous system, you bring it to reduced row echelon form and you have all zeros here and ones are sitting here. So we have x, which is like multiplied by 1 equals 0, y equals 0, and z also equals 0. So you see that we have 0, 0, 0 solution. That's not a very nice solution. And we are going to call solution like this trivial solution. What is trivial solution? Trivial solution is solution of homogeneous system which consists out of all zeros. Usually this solution is always present. Any homogeneous system has a trivial solution. Why? Because if you plug in instead of your variables in your very initial system, this one, imagine that you have zeros instead of c's. 0 here, and 0 here, all zeros. And you plug in instead of x, y, z zeros, you're going to have a true statement. So zero solution or trivial solution for homogeneous system is always present. Usually we don't care much about this solution because we kind of like to know more interesting solutions. Okay, so after we discussed the question of number of solutions, we are going to try elimination method. Okay, so let me change the color and go over elimination. Well, first I'm going to give you a system of equations, and the system is going to have 3 equations. I'm going to now use coefficient, use just numbers for coefficients, and I'm going to use labeling x1, x2, x3 for variables. Well, again, just any arbitrary system of equations. So how are we going to start solving? First, we're going to convert it into augmented matrix, which means that you copy coefficients and copy the right side. So it's 2, 2, 2, 0 here. And it's minus 2, 5, 2, 1. And 0, 1, 5, and minus 1. So that's going to be my augmented matrix. So what is going to be my procedure after I convert it? On step number 1, I'm going to look at my first row and check if my first element is non-zero, which is right now. So I'm going to maybe kind of label non-zero, which is good. I can start with my first row. In case if it's equal to 0, we are going to switch rows, and eventually you are going to find one row which is not going to have all like 0 in the first position. So, but here we are lucky, we do have non-zero. So what we are going to do with this row? We're going to turn this first element. Remember, our goal is to have 1, 0, 0, 0, 1, 0, and so on and so on. So we're going to turn it into 1. We're going to do our first step to work with it. So how are we going to do this? We are going to take row number 1 and multiply it by 1 over 2. Yeah, usually people write down divide by 2. You can do this, but normally, guys, we don't divide by 2, we multiply by 1/2. Because, like, remember, we have multiplication. Standard row operation is multiplication, not division. Well, if you do this, we are going to end up You have to do it to every element. 1, 1, 1, 0. We're not going to do anything to other rows. We're just modifying one row. And again, that's up to you. You can modify several rows at once, but I'm going to do just one, so I'm not going to confuse my operations. So my first step is done. My first one is here. Very good. Now, what I'll need to do? I'll need to take care of zeros below that one. And that's what I'm going to do now. What I see, I do have already 1 0. This one is 0 already, so I don't need to do anything. I just need to do something with this -1. And here, I'm going to use addition of one row to another one. What I'm going to do, guys, I'm going to take row number 2 and add to row number 1. Yeah, it looks like I did a stupid multiplication by 1 over 2 here to turn it into 1, and now I have to multiply it by 2 and do this like next operation. Well, you can first do this operation and then multiply by 1 over 2 if you wish. But it's not like a big deal. You can do it this way or that way. But this is a standard operation. You turn it into 1 and then kind of do this operation. So how my matrix is going to look after I do that? I copy my first row. It's not going to change. And for my second row, if I multiply this by 2, add it to -2, I'm going to get 0. Multiply my second element by 2, add it to 5, I'm going to end up with 7. Not very nice, but okay. And 2 plus 2 is 4, and 0 multiplied by 2 plus 1 is 1. And I did not do anything to the second row, the third row. Well, just because it's already like 0, 1, 5, -1. If I compare it to my goal, I already have like this one, and this one. 1 and all zeros below. Very good. I'm going to continue working with diagonal elements and try to turn all of them to 1. So my goal is right now work on elements below main diagonal. So, well, here guys, you can do two possible ways. I see that my last element is already 1. So maybe logically to shorten my time of solution, it's going to be logical to switch row number 2 and row number 3. But if you not like solving system of 3 by 3 equations and solving system of like 1000 equations by 1000, you probably are going to delegate this task to a computer. And the computer is not going to just look and find, okay, I'm lucky, I have 1 over here. Computer does not really care 1 or not 1. So I'm not going to actually do the switch. I'm going to consider my row number 2 and divide it by 7 to turn this 7 into 1. So my next operation is row number 2 equals row number 2 multiplied by 1 over 7. Remember, we never divide, we multiply by a fraction. 0, 0. If I divide by 7, which is multiplication by 1 over 7, I'll get 1. Here I'm going to have 4 over 7. Not very nice. 1 over 7 here. And my next row is going to just stay 0, 1, 5, -1. Well, very good. So now I do have this one. Next step is going to get 0 below it. What should I do? Well, I see that I have 1, and if I take my row number 2 and subtract it from row number 3, I'm going to turn this 1 into 0. So I'm going to write down row number 3 equals row number 3 minus row number 2. What result I'm going to have if I do this operation? Again, I'm copying row number 1. Row number 2. And now I'm going to subtract row number 2 from row number 3. What is interesting, guys? You see that if you subtract 0, this 0, from this 0, you're not going to change anything. And that's why we do operations in this order. So every next row is not going to break the results of the previous one. And if I do subtraction, I'm going to get 0 here, right? 1 minus 1. And the next one is not going to be very nice because I'll need to do 5 minus 4 over 7. But it's not going to be super hard. And we can always do this just like I'm going to write down here 5 minus 4 over 7. I'm going to calculate. And the last one is minus 1, which is already here, minus 1 over 7. Now I'm going to calculate this one, which is 5 by 7, 35, minus 4, 31, right? So I'm going to just eliminate it as light as I can and write down 31 over 7 here. And over here, guys, what we need to write down? We have minus 1 over 7, so it's going to be minus 8 over 7, right? Minus 8 over 7. Well, very good. So we have 1, 0, 0, 1, 0. We just need to turn our last coefficient. I'm sorry, I somehow give me a second, guys. Somehow I turned off my whiteboard. Give me a second. I'm going to stop this recording for a second and fix it. I'm using a new notepad, and it's not like I used to have my computer, but I decided it's going to be a little bit more convenient to use a notepad. But sometimes I touch wrong stuff here. So guys, sorry. We are returning back to our matrix. Now, we will need to turn this coefficient 31 over 7 into 1. How we do this? We're going to take row number 3 equals row number 3 multiplied by 7 over 31, right? If you do this multiplication, 31 is going to cancel 31, and 7 is going to cancel 7. Well, which is not going to make my matrix very beautiful, but still not bad. 0, 0, 1. And the only like little, not problem, but 8, 7 over 31, right? And the 7. So here we are going to have 2 7s in denominator, which I'm going to cancel. And maybe I'm just going to, sorry, just erase it and write down minus 8 over 31. Perfect. So, what should I do after? Well, what I have right now is just a row echelon form. I have ones on main diagonal, but some numbers above main diagonal and zeros below. After this step, there are 2 ways to continue solving this system. Remember, our goal is to get solutions for x1, x2, and x3. So way number 1 is going to be called back substitution. Some kind of 2 ways. I'm going to start with back substitution. What is back substitution? If you look at the last equation actually, if you write it down in terms of x, it's going to look like x3 multiplied by 1 equals minus 8 over 31, which is actually a solution for x3. Because you do know solution for x3, you can use it and substitute it into the second equation. Second equation looks like 1 by x2 plus 4 over 7, and instead of x3, I'm going to put minus 8 over 31 equals 1 over 7. And basically, from this equation, I can calculate x2, right? x2 equals 1 over 7 minus plus, and here I'm going to have 32, and here, well, 7 multiplied by 31. Not the number, that's okay. I don't think that we can cancel anything here. I mean, we're going to bring it to common denominator. Maybe we'll be able to do canceling, but let's check it. So, 31, that's what is missing, plus 32. I have 63. over 7 by 31. Doesn't look very nice to me. Probably happens because I did a mistake somewhere earlier. Not supposed to be that. Maybe I'm missing a minus somewhere. Let me double check. Because definitely this is way too complicated for the final answer. Mhm. I need to check it. Give me a second. Sorry, guys. I'm trying to figure out why do screen sharing. Okay, sorry. I'm hoping that it's not going to be that bad for all my lectures. So I'm sorry, I stopped at the point where we have 63 over 7 multiplied by 31, and 63 over 7 can be cancelled to 9 over 31, so that's going to be my solution for x2. Now we do have solution for x3 and x2. We can plug everything into the first equation and solve for x1. I'm going to copy my first equation, and that's going to be x1 plus x2, 9 over 31, right? x3 minus 8 over 31 and supposed to be equal to 0. Well, obviously I'm going to get x1 equals minus 1 over 31. That's going to be my answer. Now I'm going to set up the answer correct way. Minus 1 over 31, 9 over 31, and minus 8 over 31. That's my answer. It doesn't look very nice just because the coefficients of the original system are not perfect. But otherwise, it's not that bad, right? So this part is called back substitution. And like this part is called Gaussian elimination. Now, as I said, there is a second way to finish this problem. And the second way is going to bring the matrix to reduced row echelon form. This one is just row echelon form. But we can bring it to reduced row echelon form instead of back substitution. Reduced row echelon form. And that's supposed to give us the answer right away, right? Well, I think what I'm going to do, I'm going to move a little bit this way and do that reduced row echelon form around here in this space, right? So what we should do, we should continue eliminating numbers above main diagonal. But now we are going to start with the third row and we're going to use it to eliminate the coefficient from the second row and then first row and then like continue. So we started with the first row and we're eliminating down. Now we start with the last row and eliminating up. So to not get any confusion, I'm going to copy. I'm going to copy the matrix, which I kind of ended up when I was doing Gaussian elimination one more time, and then I'm going to continue working on this matrix and bringing it to reduced row echelon form. So that's a matrix, and I'm going to continue doing reduced row echelon form. So Basically, guys, my goal right now is to eliminate this element and eliminate this element, turn them into zeros. How I'm going to do this? I'm going to take row number 2 and subtract 4 over 7 of row number 3, right? If I multiply this 1 by 4 over 7 and put minus in front, it's going to eliminate this element. How my matrix is going to look after that? I'm going to start with last row. Last row is not going to change because I'm using it for my elimination. But row number 2 is going to look like, so the third element, which was 4 over 7, is going to turn it to 0. Other elements are not going to change because we do have zeros in that positions, like in position number 1, position number 2, which is why we do this algorithm in this kind of direction. If you, for example, work with row number 2 instead of row number 3, it's going to change like something. But row number 3 already has maximum zeros and just 1, 1, right? So last element is going to be what? 1 over 7 minus 4 over 7 multiplied by minus 8 over 31. I'm going to kind of calculate it a little bit later. I'm going to work with the first one and then do calculations and put correct numbers here. So what I'm going to do now, well, it would be nice to eliminate this one also. It would be very easy to do this by just subtracting row number 3 from row number 1, right? Row number 1 minus row number 3 is going to put 0 over here. And that's what I'm going to do. So element number 1 is not going to change. Element number 2 is not going to change because there are zeros correspond to them. Element number 3 is going to become 0. And if I just subtract row number 3 from row number 1, I'm going to have 8 over 31 here because it was with minus. If I subtract it, it's going to be with plus. Now I'll need to calculate this conglomeration, and basically it's supposed to be already the answer. Well, guys, what we have over here is 4, 8, 7, and 31. We already did these calculations somewhere here. I don't want to redo them again. Where they are? We had them over here. We had a 1 over 7 plus 32 over 7 multiplied by 31. This is actually the same, just like 1 over 7 plus 32, 7 over 31, which is going to result into 9 over 31. We already calculated once. I don't want to calculate it second time. So I'm going to just erase this result and just write down what we already calculated, that it's 9 over 31. Very good. So after these two row operations, our matrix is very close to reduced row echelon form. We just need to eliminate one more element, which is over here. And how to eliminate it? We are going to take row number 1 and subtract row number 2 from it, right? Since we already have 0 here and 0 here, the only element which is going to be affected is going to be this. I'm going to have 1, 0, 0, 0, 1, 0, 0, 0, 1. And numbers on the right side are not going to change. 9 over 31 here. Only number which is going to change is the top number, right? Because we are subtracting row 2 from row number 1, we are going to have 8 over 31 minus 9 over 31, which is going to produce like minus 1 over 31, right? I'm going to erase this and just write down what it's going to be. Minus 1 over 31. And guys, this is what? Reduced row echelon form, which has zeros on main diagonal, ones on main diagonal, zeros below, zeros above, below, above, and ones on main diagonal. And usually the answer is just the right side because x1 equals this, x2 equals this, x3 equals this. And of course, it's going to be the very same answer we got by back substitution. Why people are kind of not doing this to the very end? Well, again, we are not always solving equations 3 by 3. For equation 3 by 3, maybe this, by the way, the whole process of the way number 2 is called Gauss-Jordan elimination. This was Gauss-Jordan elimination, and that was Gaussian elimination and back substitution. Why people are, of course, we got the same answer, why people are using two different methods? Well, let's say usually we solve huge linear systems, thousands variables, millions variables, and of course they're solved processed by computers. And for computer time, back substitution is consuming less time than like finishing matrix and bringing it to reduced row echelon form. In tests or exams, I'm specifically going to tell you use either this way or that way, or if I don't tell you which way to use, well, you are free to choose the way you like to use. And okay, so we know how to deal with this substitution. Now I want to talk a little bit about some let's say more definitions which I missed in the beginning. So, wow, here guys, the ones which are sitting in main diagonal are called leading ones. So they're leading ones. This one. And we are going to look for which variable we do have leading ones, and we are going to call those variables leading variables. So if you have leading ones, the variables which correspond to these ones are called leading variables. Now, the rest of the variables are going to be called free variables. And over here in this specific equation, we don't have any free variables, so it's hard to tell you like what are free variables. But if we go back, let's look at example number infinitely many solutions over here, guys. If you look at this system, it's reduced row echelon form, right? We do have leading variable. So x1 is leading variable, x2 is leading variable. x3 does not have any leading one, right? So x3 here is a free variable. Free variable means that it's going to work as a parameter. Let's just like a little bit of more definitions of how we're going to name stuff. Okay, well, yes, I think that's all for today. Of course, you'll need to practice with Gaussian elimination method. And generally speaking, if one of the steps is not going to work on Gaussian elimination, as I said, for example, you take the first coefficient and it's not equal to any number, it's equal to 0, then you switch with different row which is not equal to 0. And on any step, if a 0 leading, or like if the next element on diagonal is equal to 0, you search below that element until you find something which is non-zero. If you don't find, if all elements are zeros, for example, you look for variable x2 and like all numbers there are zeros. Well, that's fine. Then you are going to move to the next one and you are going to have all these zeros there. But if you find non-zero element, you continue working with it. Okay? Well, I think that's all for today. Yeah, my answer does not look very nice, but that's okay. Okay, we'll see you in class.